Most people imagine the universe as a place governed by dramatic forces and visible energy. They think about blazing stars, violent explosions, lightning storms, black holes, and galaxies spinning through endless darkness. In the microscopic world, attention usually shifts toward particles that appear active and influential. Electrons seem exciting because they generate electricity, chemical reactions, and modern technology. Protons appear important because they determine the identity of every element in existence. Yet hidden in the center of atoms lies a particle that appears almost invisible to ordinary human experience. It has no electric charge, no glowing trail, and no obvious presence in everyday life. Because of this silence, it is easy to underestimate its importance. But the neutron, despite its neutrality, performs one of the greatest balancing acts in the entire universe. It is the quiet force that prevents matter from tearing itself apart. To understand why the neutron matters so profoundly, it is necessary to journey deep into the structure of the atom itself. Everything around us is made of atoms. Human bodies, mountains, oceans, air, stars, and distant galaxies all emerge from combinations of these tiny structures. At first glance, atoms seem stable and permanent. A rock appears solid. A table appears motionless. Steel appears strong and unbreakable. Yet beneath that illusion of stability exists an extraordinary battlefield of forces operating at scales far too small for human senses to detect. At the center of every atom lies the nucleus, an incredibly tiny region containing most of the atom's mass. Inside that nucleus are protons and neutrons packed together with unimaginable density. If an atom were enlarged to the size of a stadium, the nucleus would still be only a tiny object near the center, yet it would contain almost all the matter. Electrons would occupy vast empty regions around it. This means ordinary matter is mostly empty space, held together not by solid contact, but by invisible interactions between subatomic particles. The proton carries positive electric charge. This single property creates one of the greatest problems in atomic physics. According to electromagnetism, objects with the same charge repel each other. Two positively charged particles push apart with tremendous force. This principle is easy to observe even in everyday life. Magnets repel when similar poles face one another. Static electricity pushes certain materials apart. The same rule applies inside atomic nuclei, but with far greater intensity because the protons are compressed into incredibly small distances. This creates an enormous mystery. If protons repel one another so strongly, why does the nucleus remain together at all? Why do nuclei not explode instantly from electrical repulsion? Why does matter remain stable long enough for stars, planets, and living organisms to exist? Early physicists struggled deeply with this question because ordinary electromagnetic theory suggested that nuclei should be unstable catastrophes rather than enduring structures. The answer emerged slowly through discoveries in nuclear physics. Scientists eventually realized that another interaction, far stronger than electromagnetism at very short distances, operates inside the nucleus. This interaction became known as the strong nuclear force. Unlike gravity or electromagnetism, the strong force acts effectively only over tiny ranges. But within those tiny distances, it becomes overwhelmingly powerful. It can overpower the electrical repulsion between protons and bind nuclei together. The neutron became essential to understanding how this balance works. Because the neutron carries no electric charge, it does not contribute to the repulsive electromagnetic force inside the nucleus. Yet it still participates fully in the strong nuclear force. In effect, neutrons add attractive nuclear binding without increasing electrical repulsion. This role makes them indispensable stabilizers inside atoms. Imagine trying to build a structure using magnets that constantly push one another apart. Every additional magnet increases instability. Eventually, the structure collapses because repulsion overwhelms any attempt at organization. Now imagine adding special neutral components that strengthen the structure without increasing the repulsion. That is essentially what neutrons do inside nuclei. They provide binding strength while remaining electrically neutral. Without them, most nuclei could never survive. This truth becomes more dramatic as nuclei grow larger. The simplest atom, hydrogen, usually contains only one proton and one electron. Because there is only one proton, no proton. Proton repulsion exists inside the nucleus. Hydrogen, therefore, does not require a neutron for stability. But once additional protons appear, the situation changes rapidly. Helium contains 2 protons, carbon contains 6, oxygen contains 8, iron contains 26, uranium contains 92. As the number of protons increases, electrical repulsion grows stronger and stronger. Neutrons become increasingly necessary to counterbalance this repulsion. Larger nuclei require more neutrons than protons to remain stable. If too few neutrons are present, the nucleus becomes unstable and may undergo radioactive decay. In some cases, nuclei eject particles or radiation to achieve greater stability. In other cases, they split apart entirely. The neutron, therefore, acts as a mediator of nuclear survival. This hidden balancing role shapes the entire visible universe. Every stable heavy element depends on neutrons. Carbon, the foundation of life, survives because neutrons stabilize its nucleus. Oxygen, essential for respiration, depends on neutron balance. Calcium in bones, iron in blood, silicon in rocks, gold in jewelry, uranium in reactors. All these elements exist because neutrons allow nuclei to resist destructive repulsion. Without neutrons, the universe would contain almost nothing beyond hydrogen. Complex chemistry would never emerge. Planets composed of diverse elements would not form. Biological life would become impossible because the rich variety of stable atoms required for organic molecules would not exist. The neutron is therefore not merely another particle among many. It is one of the primary reasons complexity exists at all. The importance of this stability becomes even clearer when considering the conditions inside stars. Stars are enormous nuclear furnaces where intense pressure and temperature force nuclei together. In stellar cores, hydrogen nuclei fuse into helium through nuclear reactions. As stars evolve, heavier elements form through additional fusion processes. Yet every stage of this cosmic element building depends on neutron balance. Inside stars, nuclei constantly face extreme energy conditions. High temperatures cause violent collisions among particles. Without stabilizing forces, nuclei would fragment easily under such circumstances. Neutrons help maintain the integrity of atomic nuclei even within these extreme environments. They allow stars to build increasingly complex elements over millions or billions of years. When massive stars die, the importance of neutrons becomes even more dramatic. In supernova explosions, stars release enormous amounts of energy in catastrophic collapses. During these events, huge numbers of neutrons flood outward through surrounding matter. Nuclei rapidly capture neutrons, forming heavier and heavier elements through processes known as nucleosynthesis. Many of the heaviest elements in the universe were created during these neutron-rich explosions. This means the atoms inside human bodies were shaped by neutron-driven events long before Earth existed. The calcium in bones, the iodine in thyroid glands, and the iron carried through bloodstreams all emerged from ancient stellar environments where neutron interactions governed nuclear formation. Human beings are therefore deeply connected to neutron physics at the most fundamental level. The stability of matter and the existence of life both depend on processes involving these silent particles. The neutron's hidden role also transformed human understanding of science itself. For centuries, atoms were poorly understood. Ancient philosophers imagined matter as indivisible units, but they possessed no evidence about internal structure. By the 19th century, scientists recognized that atoms existed, yet their composition remained mysterious. The discovery of the electron revealed that atoms contained smaller particles, but many questions persisted. One major puzzle involved atomic mass. Protons alone could not explain the observed masses of nuclei. Scientists suspected another particle must exist inside atoms. In 1932, physicist James Chadwick confirmed the existence of the neutron through groundbreaking experiments. This discovery revolutionized nuclear physics. Suddenly, atomic structure became clearer. Isotopes could be explained as atoms containing different numbers of neutrons. Nuclear reactions became understandable. Radioactivity made more sense. The entire field of nuclear science accelerated rapidly after the neutron's discovery because scientists finally possessed the missing piece needed to explain nuclear stability. The neutron also revealed how delicate the balance of nature truly is. Atomic stability depends on precise relationships among forces and particles. Too many neutrons can destabilize nuclei just as surely as too few. This delicate equilibrium governs the existence of every stable element. Consider uranium, one of the heaviest naturally occurring elements. Its enormous nucleus contains many protons, creating tremendous electrical repulsion. Large numbers of neutrons help stabilize the nucleus, but even this balance remains fragile. Certain uranium isotopes become unstable enough that absorbing an extra neutron can trigger nuclear fission, splitting the nucleus into smaller fragments while releasing immense energy. This discovery led humanity into the nuclear age. Nuclear reactors rely on controlled neutron interactions to produce energy. When nuclei split during fission, they release additional neutrons that can trigger further reactions. Under controlled conditions, this process generates electricity for cities and industries. Under uncontrolled conditions, it produces devastating explosions. Thus, the neutron became central not only to natural cosmic processes, but also to human civilization. It enabled nuclear medicine, scientific research, energy production, and unfortunately warfare. The same particle that silently stabilizes atoms also made possible some of humanity's most powerful technologies. Yet, despite these dramatic applications, the neutron remains deeply mysterious. Although electrically neutral overall, it is not truly simple. Modern particle physics reveals that neutrons are composed of smaller particles called quarks. Specifically, a neutron contains one up quark and two down quarks bound together by gluons through the strong interaction. Inside the neutron, energy fluctuates constantly through quantum effects. Virtual particles appear and disappear. Fields interact dynamically. What seems like a calm neutral particle from the outside is internally a storm of quantum activity. This discovery shattered the old image of particles as tiny solid objects. Instead, modern physics describes them as complex excitations within deeper quantum fields. The neutron also possesses a finite lifetime outside nuclei. Free neutrons do not survive forever. After roughly 15 minutes, an isolated neutron decays into a proton, electron, and antineutrino through a process called beta decay. This fact reveals another profound truth about stability in nature. Even the neutron itself depends on environmental context. Inside stable nuclei, neutrons can survive indefinitely. Alone in space, they eventually transform into other particles. This transformation connects neutrons to one of the deepest principles in physics, the constant evolution of matter and energy. Stability is never absolute. Everything exists within dynamic relationships governed by physical laws. The neutron helps maintain those relationships at nuclear scales, yet it too participates in the universe's endless transformations. The story of the neutron, therefore, becomes much larger than atomic physics alone. It becomes a story about hidden balance throughout reality. Human beings often focus attention on visible power and obvious activity. Bright stars attract more fascination than invisible particles. Explosions seem more dramatic than silent stability. Yet the universe repeatedly demonstrates that unseen balancing forces may be more important than visible displays of energy. Gravity quietly shapes galaxies across billions of light years. Dark matter invisibly influences cosmic structure. DNA silently encodes biological information inside living cells. Likewise, neutrons invisibly stabilize matter itself. The universe depends not only on powerful forces, but also on subtle equilibrium. This lesson extends beyond physics into philosophy and human understanding. Stability often requires unseen support systems. Civilizations depend on invisible infrastructure. Ecosystems depend on delicate balances among organisms. Human bodies depend on countless unnoticed biological processes occurring every second. The neutron becomes a symbol of how essential hidden structures can be. Even in modern scientific research, neutrons continue revealing new knowledge about reality. Scientists use neutron scattering techniques to study materials and molecular structures. Because neutrons carry no electric charge, they penetrate matter differently from charged particles or light. This allows researchers to investigate internal structures hidden from ordinary observation. Neutron studies help scientists understand superconductors, magnetic materials, proteins, liquids, and complex Arabic, Saida Arabic, Noon Arabic, Tain Arabic, Ta Arabic, Farsi structures. In medicine, neutron-related technologies assist cancer treatments and imaging techniques. In cosmology, neutron behavior influences theories about the early universe and stellar evolution. The quiet particle at the center of atoms continues shaping cutting-edge science in unexpected ways. Perhaps the most astonishing neutron structures in existence are neutron stars. When massive stars exhaust their nuclear fuel, gravity can crush them so intensely that electrons and protons combine into neutrons. The result is a neutron star, an object with extraordinary density. A single teaspoon of neutron star matter could weigh billions of tons on Earth. These stars demonstrate matter pushed to extreme limits. Under such pressure, neutrons dominate almost completely. Entire stellar remnants become gigantic nuclear structures governed by neutron physics. Some neutron stars rotate hundreds of times per second and emit beams of radiation across space. Others generate magnetic fields trillions of times stronger than Earth's. They stand among the most extreme objects known in the universe. Yet even these extraordinary stars originate from the same quiet particle that stabilizes ordinary atoms. The neutron connects the smallest scales of matter to some of the largest and most violent events in the cosmos. It bridges quantum mechanics, nuclear physics, astrophysics, and cosmology in one continuous story. Human beings rarely think about neutrons in daily life because their role remains hidden beneath ordinary perception. People see colors, hear sounds, and feel textures, but none of these senses directly reveal nuclear stability. The atom appears calm and permanent, even though it depends on intense internal forces. The neutron performs its task so effectively that matter seems naturally stable, causing most people to overlook the incredible balancing act occurring inside every nucleus. But once that hidden world is understood, ordinary reality appears transformed. Every object becomes a miracle of equilibrium. Every atom becomes a triumph over repulsive forces. Every breath, every living cell, every solid structure becomes evidence of neutron stabilization operating continuously across the universe. The universe appears rich with variety. Mountains rise from planetary surfaces, oceans flow across continents, stars burn with different colors, and living organisms display astonishing complexity. Human beings are surrounded by materials so diverse that it becomes easy to assume this abundance is natural and inevitable. Gold, oxygen, carbon, uranium, calcium, silicon, iron, and countless other elements seem like permanent features of existence itself. Yet beneath this apparent permanence lies a fragile truth. Most matter in the universe exists only because of one silent particle that carries no electric charge at all. Without the neutron, nearly every complex atom would fail to survive. The rich architecture of matter would collapse into simplicity. The universe would become almost empty of the chemical diversity required for planets, oceans, biology, and civilization. The neutron is therefore not merely part of atomic structure. It is one of the main reasons complexity exists anywhere in reality. At first glance, the neutron seems unremarkable. Unlike the electron, it does not generate electricity or chemistry directly. Unlike the proton, it does not define the identity of an element. It possesses no electric charge and often receives little attention in basic descriptions of atoms. Yet this neutrality is precisely what gives the neutron its extraordinary importance. It performs a stabilizing role that allows nuclei to exist despite the enormous repulsive forces operating within them. To understand why most matter could not exist without neutrons, it is necessary to look deeply into the nature of atomic nuclei. Every atom contains a nucleus composed of protons and, in most cases, neutrons. Protons carry positive electric charge. According to electromagnetic physics, positive charges repel one another strongly. This means that every proton inside a nucleus pushes against every other proton. The larger the nucleus becomes, the stronger this repulsion grows. This creates a profound problem for nature. If nuclei contained only protons, most atoms would instantly tear themselves apart. The repulsive force between positively charged particles would become overwhelming. Only the simplest nuclei could survive. Hydrogen, with a single proton, would remain stable because no proton. Proton repulsion exists within it. But beyond hydrogen, atomic complexity would collapse rapidly. The neutron changes everything. Because it carries no electric charge, it adds mass and participates in nuclear binding without increasing electromagnetic repulsion. Neutrons interact through the strong nuclear force, one of the most powerful interactions in existence. This force acts at extremely short distances and binds protons and neutrons together inside nuclei. By contributing attractive nuclear interactions without adding electric repulsion, neutrons create the balance required for stable matter. Imagine trying to build a city where every building violently pushes against every neighboring structure. No stable architecture could emerge. Walls would collapse, foundations would fail, and organized systems would disintegrate. Now imagine introducing components that strengthen connections without increasing the repulsive pressure. Stability suddenly becomes possible. This is essentially what neutrons do inside atomic nuclei. They are the silent stabilizers that allow complex structures to survive. Hydrogen reveals how limited a neutronless universe would be. Ordinary hydrogen consists of one proton and one electron. It is stable because there are no multiple protons competing within the nucleus. But the moment additional protons appear, repulsion becomes significant. Helium contains 2 protons, carbon contains 6, oxygen contains 8, iron contains 26, gold contains 79. Uranium contains 92. Without neutrons, these nuclei could not remain bound together. This means that nearly every element heavier than hydrogen depends fundamentally on neutrons. The universe without neutrons would therefore contain almost no chemistry beyond the simplest possible reactions. Water could not exist because oxygen nuclei would not survive. Organic molecules could not form because carbon nuclei would collapse. Rocky planets would never emerge because silicon and iron would be absent. Biological systems would become impossible because the essential elements required for life would not exist. The neutron, therefore, acts as the hidden architect of material diversity. Every stable heavy element represents a triumph of neutron stabilization over electromagnetic repulsion. The richness of chemistry itself depends on this balance. Carbon provides one of the clearest examples. Life on Earth is carbon-based because carbon atoms possess remarkable chemical flexibility. Carbon can form long chains, rings, and complex molecular structures capable of storing information and supporting biological processes. DNA, proteins, fats, sugars, and countless biological compounds all depend on carbon chemistry. Yet carbon nuclei remain stable only because neutrons help bind their protons together. Without neutrons, carbon could not exist. Without carbon, biology as humans know it would disappear entirely. Oxygen offers another example. Every breath taken by living organisms depends on oxygen atoms. Water molecules require oxygen nuclei. Respiration depends on oxygen chemistry. Yet oxygen contains 8 protons packed into a tiny nucleus. The repulsive electrical force among these protons would destroy the nucleus without stabilizing neutrons. Thus, every ocean, river, cloud, and living cell owes its existence partly to neutron balance inside oxygen atoms. The same truth extends throughout the periodic table. Calcium strengthens bones. Iron carries oxygen in blood. Phosphorus helps form DNA and cellular energy systems. Sodium and potassium enable nerve signals. Silicon forms rocks and technological materials. Copper conducts electricity. Gold remains chemically stable enough for jewelry and electronics. All these elements require neutrons for nuclear stability. Without neutrons, stars themselves would also behave differently. Stellar evolution depends on nuclear fusion, the process through which lighter nuclei combine into heavier nuclei under extreme temperatures and pressures. In stars like the Sun, hydrogen nuclei fuse into helium. Over time, larger stars produce increasingly heavy elements through additional fusion stages. These processes rely on stable nuclei existing long enough to participate in reactions. Without neutron stabilization, fusion pathways would become severely limited. Stars might still burn hydrogen temporarily, but the production of heavier elements would collapse. The universe would remain chemically primitive. This would profoundly alter cosmic evolution. Rocky planets like Earth form from heavy elements produced inside stars and distributed through supernova explosions. Without heavy elements, planets composed of metals and silicate rocks would not exist. Complex atmospheres would fail to develop. Magnetic fields generated by metallic cores would disappear. Geological activity would change completely. Even the possibility of life would shrink dramatically. Biology depends not only on carbon and oxygen, but also on a wide range of trace elements. Enzymes rely on metals such as iron, zinc, copper, and magnesium. Cellular communication depends on ions like sodium and potassium. Energy transfer involves phosphorus, containing molecules. None of this biochemical complexity could arise in a neutronless universe. The neutron, therefore, stands behind every layer of material organization in existence. It stabilizes nuclei, enabling diverse elements. Diverse elements enable chemistry. Chemistry enables planets, atmospheres, oceans, and biological systems. Biological systems eventually enable consciousness capable of reflecting on the universe itself. In this way, the neutron indirectly contributes to the existence of observers who can ask scientific questions. The story becomes even more astonishing when examining how heavy elements form in the cosmos. Inside ordinary stars, fusion can build nuclei only up to certain limits. Many of the heaviest elements require environments rich in neutrons. These conditions emerge during supernova explosions and neutron-star collisions, among the most violent events in the universe. During a supernova, massive stars collapse catastrophically after exhausting their nuclear fuel. Temperatures and pressures rise to extraordinary levels. Vast numbers of neutrons flood through surrounding matter. Atomic nuclei rapidly capture these neutrons in processes that build heavier and heavier elements. Gold, platinum, uranium, and many other heavy atoms originate from these neutron-rich events. This means that some of the atoms inside human bodies were forged during ancient cosmic catastrophes dominated by neutron physics. The gold in jewelry, the iodine in the human thyroid, and the uranium buried underground all owe their existence to environments where neutrons transformed simpler nuclei into complex elements. Billions of years ago, modern astronomy has revealed that neutron-star collisions are especially important for heavy element production. When neutron stars merge, enormous quantities of neutron-rich material scatter across space. These collisions create some of the heaviest elements in the universe. In a profound sense, human civilization depends on matter shaped by ancient neutron-riven cosmic violence. Yet, despite this immense importance, the neutron remained undiscovered until the 20th century. Scientists originally struggled to explain atomic structure because protons and electrons alone could not account for observed masses and nuclear behavior. The discovery of the neutron by James Chadwick in 1932 solved many of these mysteries and transformed physics forever. Once the neutron was understood, isotopes suddenly made sense. Elements could exist in multiple forms containing different numbers of neutrons while retaining the same number of protons. Carbon-12 and carbon-14, for example, are both carbon because they contain 6 protons, yet they differ in neutron number. Some isotopes remain stable while others undergo radioactive decay depending on neutron-proton balance. This revealed how delicate nuclear stability truly is. Too few neutrons destabilize nuclei because proton repulsion dominates. Too many neutrons can also destabilize nuclei by disrupting nuclear balance. Nature therefore operates within narrow conditions that permit stable matter. The existence of stable elements becomes even more remarkable when considering the forces involved. The strong nuclear force binds nuclei together, yet it operates only across tiny distances. Electromagnetic repulsion continuously pushes protons apart. Quantum mechanics introduces additional complexities through uncertainty and particle behavior. Stable matter emerges from an intricate balance among these competing effects. The neutron sits at the center of this balance. It acts neither as a passive bystander nor as a simple filler particle. It is an active participant in maintaining nuclear integrity. Every stable heavy nucleus represents an equilibrium achieved partly through neutron presence. The consequences of neutron absence would therefore extend far beyond chemistry. Entire cosmic structures would differ. Planetary systems might never resemble those known today. The possibility of intelligent life could vanish completely. The universe might remain a thin sea of hydrogen gas with limited complexity and little structure beyond stars. Even human technology depends deeply on neutron-enabled matter. Modern electronics require silicon, copper, gold, and rare earth elements. Buildings require iron and calcium, rich materials. Medical systems rely on diverse chemical compounds. Agriculture depends on nitrogen, phosphorus, and potassium cycles. Every industrial civilization emerges from elemental diversity made possible by neutrons. The neutron also enables some of humanity's most powerful scientific tools. Nuclear reactors depend on neutron interactions during fission reactions. When heavy nuclei absorb neutrons, they may split into smaller nuclei while releasing enormous energy and additional neutrons. Controlled chain reactions generate electricity for millions of people. In medicine, neutron-based technologies assist cancer treatments and imaging systems. In research laboratories, neutron scattering allows scientists to probe the internal structures of materials, proteins, and magnetic systems. Because neutrons carry no electric charge, they penetrate matter differently from charged particles, providing unique scientific insights. At deeper levels, the neutron also reveals profound truths about the nature of reality itself. Although electrically neutral overall, neutrons are not fundamental particles. Modern physics shows they consist of smaller entities called quarks held together by gluons. Inside the neutron, quantum fields fluctuate constantly. Energy transforms dynamically. Virtual particles emerge and disappear. This means the neutron's apparent simplicity hides extraordinary complexity. What appears silent and neutral at human scales contains intense internal activity at quantum scales. The same principle applies throughout nature. Reality often conceals its deepest structures beneath surfaces that seem calm and ordinary. Neutron stars provide one of the most dramatic examples of neutron dominance in the cosmos. When massive stars collapse under gravity, protons and electrons combine into neutrons. Entire stellar remnants become gigantic spheres composed mostly of neutron matter. These stars possess densities so extreme that a small amount of material would weigh billions of tons on Earth. Neutron stars reveal matter compressed to astonishing limits. The same particle that stabilizes ordinary atoms can also dominate entire stars. Some neutron stars rotate hundreds of times per second and emit beams of radiation across space. Others generate magnetic fields of unimaginable strength. They stand among the most extreme objects known to science, yet they originate from the same quiet neutron hidden inside every atom. The neutron, therefore, connects the microscopic and cosmic worlds in a continuous chain. It stabilizes nuclei, enables elements, shapes stars, drives supernova, forms neutron stars, and influences the evolution of galaxies. Few particles possess such broad importance across so many scales of existence. Perhaps the most profound lesson of the neutron is that neutrality does not mean insignificance. Human beings often associate importance with visibility, charge, brightness, or dramatic activity. Yet the neutron demonstrates that silent stabilizing forces may be even more essential than obvious power. Without neutrons, complexity collapses. The richness of the universe disappears. Every object around us becomes evidence of neutron balance. Every breath depends on neutron, stabilized oxygen. Every heartbeat depends on iron atoms stabilized by neutrons. Every thought occurring inside the human brain depends on chemical systems built from neutron-supported elements. Civilization itself rests on atomic stability maintained by these silent particles. The neutron's hidden role reminds humanity that existence depends not only on energy and motion, but also on equilibrium. The universe survives through delicate balances among forces, particles, and interactions. Remove the neutron from that balance, and the grand architecture of matter dissolves into simplicity. The stars may still shine, but the universe would lose the diversity required for worlds, oceans, life, and consciousness. The universe often hides its greatest secrets behind silence. Some forces announce themselves with violence and brilliance. Supernova explosions can outshine entire galaxies. Black holes bend light and distort space itself. Lightning tears through skies with visible power. Even at the atomic level, electrons race through matter, creating electricity, chemistry, and technology. Protons determine the identity of every element and sit at the center of atoms with unmistakable importance. Yet among all these dramatic features of nature exists a particle that appears almost invisible to ordinary experience. It carries no electric charge, it produces no direct light, it remains unnoticed in everyday life. Still, this quiet particle helped shape stars, forge elements, and build the structure of reality itself. The neutron, despite its neutrality, became one of the main architects of the cosmos. To understand the neutron's hidden influence, it is necessary to travel back to the earliest moments of the universe. Immediately after the Big Bang, the cosmos was unimaginably hot and dense. Matter, as humans know, it did not yet exist. There were no atoms, no stars, no planets, and no galaxies. Instead, the universe contained a turbulent sea of energy and elementary particles colliding at enormous speeds. In these first moments, temperatures were so extreme that ordinary atomic nuclei could not survive. Particles constantly formed and disappeared through violent interactions. Among the particles emerging in this chaotic environment were protons and neutrons. The balance between them would eventually determine the chemical future of the universe. Neutrons played a crucial role during this early era because they participated directly in the formation of the first nuclei. As the universe expanded, temperatures gradually cooled. Conditions eventually became stable enough for protons and neutrons to combine into simple nuclei through a process known as primordial nucleosynthesis. This stage produced the earliest forms of hydrogen and helium, along with tiny amounts of other light elements. Without neutrons, even this first step toward cosmic structure would have failed. Helium nuclei require neutrons to stabilize the two positively charged protons inside them. If neutrons had not existed, the early universe would have remained dominated almost entirely by isolated hydrogen nuclei. The formation of more complex atomic structures would have become vastly more difficult. This early neutron activity shaped everything that followed. The ratio of hydrogen to helium produced in the first minutes after the Big Bang influenced the formation of stars and galaxies billions of years later. In a profound sense, the neutron helped determine the large-scale structure of the observable universe long before planets or life existed. As gravity slowly gathered matter together, the first stars began to form. These stars became the next great stage of neutron influence. Inside stellar cores, temperatures and pressures rose to extraordinary levels. Hydrogen nuclei collided with such force that nuclear fusion became possible. Protons fused together, eventually forming helium and releasing enormous amounts of energy. Stars shine because of these nuclear reactions. The Sun itself is powered by fusion occurring deep within its core every second. Yet neutron behavior is deeply connected to these reactions. During fusion processes, protons sometimes transform into neutrons through weak nuclear interactions. These transformations allow stable nuclei to form inside stars. Without neutron involvement, many stellar fusion pathways would not function correctly. The neutron therefore helped stars become stable energy, producing systems rather than chaotic collections of plasma. It contributed to the balance that allowed stars to burn for millions or billions of years. This stellar stability proved essential for the later emergence of planets and life. But the neutron's role inside stars extended far beyond maintaining stability. Stars also became cosmic factories for element creation, and neutrons were central to that process. In the cores of massive stars, fusion gradually produced heavier elements over time. Hydrogen became helium. Helium fused into carbon. Carbon led toward oxygen, neon, silicon, and eventually iron. Each stage required increasingly extreme conditions. These reactions depended on the delicate balance of nuclear forces inside atomic nuclei. Neutrons stabilized growing nuclei as additional protons increased electromagnetic repulsion. Without neutrons, heavy nuclei would fly apart before stable elements could emerge. The neutron therefore allowed stars to construct the periodic table piece by piece. Carbon became one of the most important products of stellar nucleosynthesis. Every known form of life depends on carbon chemistry because carbon atoms can form highly complex molecular structures. Yet carbon nuclei require neutrons for stability. This means the neutron indirectly enabled the chemistry of life itself. Oxygen formed through similar processes inside stars. Every breath taken by living organisms depends on oxygen, atoms forged in ancient stellar interiors where neutron stabilization allowed oxygen nuclei to survive. Calcium in bones, iron in blood, and silicon in rocks all emerged through neutron-assisted nuclear processes within stars. The neutron's influence became even more dramatic during the deaths of massive stars. When giant stars exhaust their nuclear fuel, gravity overwhelms the outward pressure generated by fusion. The star collapses catastrophically in an explosion known as a supernova. These events rank among the most violent phenomena in the universe. During a supernova, temperatures rise so high and pressures become so intense that enormous numbers of neutrons flood through surrounding matter. Nuclei rapidly capture neutrons in a process that creates many of the heaviest elements in existence. Gold, platinum, uranium, thorium, and numerous other heavy elements owe their existence to these neutron-rich explosions. This process transformed the universe chemically. Before stars and supernova, the cosmos contained mostly hydrogen and helium. After billions of years of stellar evolution and neutron-driven nucleosynthesis, galaxies became enriched with complex elements capable of forming planets and biological systems. The atoms inside human bodies therefore carry a cosmic history shaped by neutrons. The iron circulating through blood was forged inside ancient stars. The calcium in bones originated in stellar interiors. Even rare elements used in modern technology were created through neutron interactions during supernova explosions billions of years ago. In this sense, human beings are products of neutron-driven cosmic evolution. Every living organism depends on elements created through nuclear processes governed partly by neutron behavior. The neutron did not merely stabilize matter in a passive way. It actively participated in building the chemical foundation of life. The neutron also shaped some of the strangest objects in the universe, neutron stars. After certain supernova explosions, the collapsing core of a massive star becomes so compressed that electrons and protons combine into neutrons. Matter transforms into an extraordinary state, dominated almost entirely by neutron density. A neutron star is one of the most extreme structures known to science. These objects contain masses comparable to the Sun compressed into regions only a few kilometers wide. Their densities become so enormous that a teaspoon of neutron star material could weigh billions of tons on Earth. Gravity inside neutron stars is almost beyond human imagination. Atomic structures collapse completely under pressure. Matter behaves in ways still not fully understood by physicists. Some neutron stars spin hundreds of times each second while emitting beams of radiation across space. Others possess magnetic fields trillions of times stronger than Earth's magnetic field. Yet despite their cosmic scale, neutron stars are built from the same particle hidden inside ordinary atoms. The neutron therefore links the smallest structures in matter to some of the largest and most powerful objects in the universe. It bridges quantum physics and astrophysics in one continuous story. The neutron's role in shaping reality also extends into the formation of planets. Rocky planets like Earth, formed from heavy elements produced inside stars and distributed through supernova explosions. Without neutron-assisted nucleosynthesis, these elements would not exist in sufficient quantities. Earth's iron core, silicon, rich crust, oxygen, filled atmosphere, and carbon-based life all depend on neutron-created elements. Mountains, oceans, minerals, and biological organisms are therefore indirect products of neutron physics, operating across billions of years of cosmic evolution. Even modern civilization depends deeply on neutron-shaped matter. Metals used in buildings, electronics, transportation, and communication all rely on elements forged through neutron-driven stellar processes. Gold used in electronics, uranium used in reactors, copper used in wires, and silicon used in computer chips all emerged because neutrons enabled complex nuclei to exist. The neutron's hidden role becomes even more fascinating when examined through modern particle physics. Although neutrons appear electrically neutral and relatively simple. They are actually composed of smaller particles called quarks. Specifically, a neutron contains one up quark and two down quarks bound together by gluons through the strong nuclear interaction. Inside the neutron, quantum fields fluctuate constantly. Virtual particles emerge and vanish. Energy transforms dynamically within an invisible storm of microscopic activity. What appears silent and stable at ordinary scales hides intense complexity at deeper levels. This discovery changed humanity's understanding of matter itself. Particles were no longer viewed as tiny solid objects, but as dynamic excitations within quantum fields. The neutron became part of a far richer and stranger picture of reality than earlier generations could imagine. The neutron also revealed how delicate the structure of existence truly is. Stable matter depends on precise relationships among forces and particles. If the neutron's mass differed slightly relative to the proton, nuclear reactions inside stars would change dramatically. Element formation could fail. Life, supporting chemistry, might never emerge. This sensitivity suggests that the universe exists within narrow physical conditions, allowing complexity to arise. The neutron occupies a critical position within those conditions. A small change in neutron properties could produce a radically different cosmos. Scientists continue studying neutrons today because they remain essential to understanding nature. Neutron scattering techniques allow researchers to investigate materials, biological molecules, magnetic systems, and quantum structures. Because neutrons carry no electric charge, they can penetrate matter differently from charged particles, revealing hidden internal arrangements. Neutron research contributes to medicine, engineering, chemistry, condensed matter physics, and cosmology. Reactors generate neutrons for scientific experiments. Particle accelerators investigate neutron structure. Astronomers study neutron stars to probe the limits of matter under extreme gravity. The neutron also shaped human history through nuclear technology. Nuclear reactors rely on neutron-induced chain reactions. When heavy nuclei absorb neutrons, they may split apart through nuclear fission, releasing enormous energy and additional neutrons. Controlled fission powers electrical grids. Uncontrolled fission created nuclear weapons. Thus, the neutron became both a source of scientific advancement and existential danger. Humanity's ability to manipulate neutron interactions transformed geopolitics, energy systems, and warfare in the 20th century. Few particles have influenced civilization so directly. Yet despite all these extraordinary effects, the neutron remains hidden from ordinary human awareness. People rarely think about the nuclear stability sustaining every object around them. A glass of water seems simple, but the oxygen atoms inside it survive because neutrons stabilize their nuclei. Human bones appear solid, yet calcium nuclei depend on neutrons. Every breath, every heartbeat, and every thought occurs within matter shaped fundamentally by neutron physics. This hidden nature gives the neutron philosophical significance as well as scientific importance. Human beings often focus attention on visible power and dramatic events. Brightness, movement, and charge attract notice. But the neutron demonstrates that quiet stabilizing forces may be equally or even more important than visible activity. The universe depends not only on explosive energy, but also on balance. Galaxies remain organized through gravitational equilibrium. Ecosystems survive through delicate biological interactions. Human bodies function through countless unseen cellular processes. Likewise, atoms survive because neutrons silently maintain nuclear stability. The neutron teaches that neutrality does not mean insignificance. Silence does not imply weakness. Some of the most important structures in existence depend on forces and particles hidden beneath ordinary perception. Every stable atom beyond hydrogen stands as evidence of neutron influence. Every heavy element forged inside stars reflects neutron participation. Every rocky planet, every ocean, every living organism, and every civilization emerges partly from neutron-driven cosmic history. The neutron therefore helped shape not only matter, but the possibility of complexity itself. It guided the evolution of stars, enabled the formation of elements, stabilized nuclei, and contributed to the emergence of life, supporting worlds. From the first minutes after the Big Bang to the interiors of neutron stars, from ancient supernova explosions to modern human technology, the neutron has quietly shaped reality at every stage. The universe often celebrates dramatic phenomena, but beneath that visible spectacle lies an invisible architecture of balance. The neutron stands at the center of that hidden architecture. It carries no electric charge, yet it carries the weight of stars, planets, chemistry, and existence itself.